Hello everyone, in this video we are going to evaluate the rather intimidating looking integral that we see on the screen here. It's the integral from minus a to a of the square root of a squared minus x squared over x minus b cubed, where a and b are real positive parameters and a is less than b. So we're going to approach this using contour integration, and therefore we need to sort of promote our integrand to a complex function and then decide which path in the complex plane we're going to integrate around. The most natural choice of complex function to introduce here would be f of z, as I've defined it, a squared minus z squared to the half over z minus b cubed. Now notice that a squared minus z squared to the half is actually a multi-valued complex function, in contrast to the square root of a squared minus x squared as appears in the original integrand, which by definition is real and positive. That already suggests that we're going to have to take care to make a suitable branch cut in the complex plane before we start trying to actually evaluate our integral. Now, if you're already confident that you know how to deal with branch cuts, then that's great. If not, then have a look at my previous video in which I consider branch cuts of this particular function, so that might be helpful. Anyway, notice that I've factorized the numerator of f of z using the difference of two squares, just to really highlight the point that there are two branch points of this function at z equals a and z equals minus a. Now, of course, the key result that we're going to need to evaluate our integral is the residue theorem, which I've stated here. So the integral around a closed contour C traversed in the anti-clockwise sense of f of z is 2 pi I times the sum of the residues of f of z at all of the various poles of f of z that lie inside the curve C. You can already see quite easily that just by looking at the form of f of z, there's a z minus b cubed on the denominator, and therefore we have a pole of order 3 at z equals b. So we're going to need to decide what path in the complex plane to do our integral around, but before we can decide that, we need to choose the appropriate branch cut, and I'm going to choose to make a branch cut as illustrated in the diagram here, where I exclude the region of the complex plane along the real axis from minus a to a. Why am I choosing to do a branch cut that way rather than make two different branch cuts going off to infinity along the negative and positive real axes? Well, it's because eventually we're going to be integrating over some closed curve in the complex plane, and we want that closed curve to involve a segment that looks something like this, because if you think about the integral of f of z over that part of the complex plane, if the imaginary part becomes negligibly small, then you're going to just recover I, in other words, the integral that we initially defined, that real integral that we're trying to evaluate. If you were to then integrate over some closed loop that brings you back to the other side of the branch cut, immediately below that branch cut, let's say you're integrating this way above and this way below, then if f of z had exactly the same value above and below the branch cut, those two contributions would cancel, and you would get an equation that essentially said 0 equals 0 at the end, because everything cancels out. But by placing that branch cut there, we guarantee that f of z has different values above and below the branch cut, and therefore things don't cancel and we get a result that's actually useful. So we'll see in much more detail how that all works out later in the video. So as a first attempt at coming up with a suitable contour, let's try this, where we integrate over that portion of the real axis, or the portion just above the real axis and just below the real axis, as we discussed before, and then we close up the curve with circular paths centered on the two branch points minus a and a. It turns out, however, that if you try to apply the residue theorem to work out the value of I using this particular contour, you end up concluding that I equals 0, which is definitely not right. I is non-zero. Without going into all the details, because we're going to cover them later properly, essentially the reason why you end up concluding that it's 0 is that the contribution to the integral of this part of the curve, the straight line above the branch cut, ends up being I. The contribution to the integral below the branch cut also ends up being I. And if you take the limit as the radius of these circles goes to 0, then you find that the circles don't contribute anything to the integral at all. And because there are no poles inside that curve, you would set the 2 pi I times the sum of the residues to 0, and then you would conclude that 2i is 0 and hence I is 0. So what's actually gone wrong there? Well, it's basically the fact that f of z is not analytic inside the curve that we've integrated around because of the presence of those two branch points, and therefore the residue theorem doesn't actually apply. So in an attempt to fix this issue, we are going to try integrating around this somewhat more complicated looking contour, which is nevertheless just a variation on the original contour that we proposed. So essentially we've modified the original contour in such a way that f of z is now analytic everywhere inside the contour other than at that isolated singularity at z equals b on the real axis. We've essentially split up this horizontal part of our original curve, and we have gone vertically off to infinity along the imaginary axis, and then integrated all the way around this huge circle, and then come back and continued the original curve in the same way that we did originally. The key difference here now is, of course, that the interior of the curve no longer contains the branch points, right? The interior of the curve is sort of all of this stuff, which I'm now shading in, as opposed to what it was before, which was this bit here. Now I've labeled the various different segments of the curve C1 up to C8, except the one seems to have gone missing. This should have been labeled C1. And therefore, if I were to write the residue theorem in a more specific way to this particular curve, it would be the integral over C1 plus the integral over C2 plus all of the various integrals over all the various parts up to the integral over C8 is 2 pi I times the residue at the only pole of the function which is inside the curve, which is B. Our next goal then is going to be to show that most of those integrals, the integrals over most of the various segments of the curve, are either zero or cancel each other out. This is often the case with contour integrals. A lot of the work is in just showing that a lot of the various bits go to zero. In order to show that they go to zero, I do need to specify a couple of other parameters on this diagram. First of all, we're going to say that the radius of these small circles is lowercase r, and we're going to say that the radius of the large circle is capital R, and we're going to imagine taking the limit as small r goes to 0 and capital R goes to infinity. So let's think about C1 first of all, that big circular part of the curve whose radius is going off to infinity. So we're going to handle C1 by parameterizing the value of our complex number z as the radius of the circle, capital R, times e to the I theta, where theta is just the angle that z makes with the positive real axis, goes around from 0 to 2 pi. And as a reminder, we are letting r go to infinity. What we're going to do is consider the following quantity, the modulus of z times f of z on the curve C1 where z equals r e to the I theta. Why are we doing this? Well, it's because what we're essentially doing is a line integral around that big circle, right? The circumference of that circle is 2 pi times capital R. The circumference therefore scales as r, otherwise known as just the modulus of z, while f of z is of course just the integrand itself. So if you consider the quantity modulus of z times modulus of f of z, if we can show that that quantity goes to 0 everywhere on the curve C1, then we've proved that the line integral itself goes to 0. This is a sufficient condition to prove that the line integral goes to 0. It's not a necessary condition, but it is a sufficient condition. But when it does work, it makes life a little bit easier, and we're lucky here because, as it turns out, the modulus of z, f of z, does go to 0. So let's prove that. Well, the modulus of z itself, because z is r e to the I theta, it's just r, which is a positive real number by definition. Then this is going to be multiplied by the modulus of f of z. Now if we go back to the definition of f of z up here, focus on the numerator. When the modulus of z is huge because we're letting r go to infinity, that a squared minus z squared is approximately just minus z squared. And because we're only caring about magnitudes here, without pluses and minus signs and phases and things like that, we can just replace the numerator with r squared to the power of a half. On the denominator, by the same argument, you can ignore this b here. When z gets really huge in magnitude, the magnitude of z minus b cubed will be approximately just r cubed. And then when we expand out the brackets, we get r times and then r over r cubed, which overall is 1 over r, and that clearly tends to 0 as r goes to infinity. Next up, let's deal with the small circles, i.e. C4 and C6. So how are we going to parameterize z on C4 first of all? Well, it's still just a circle, but its center is no longer the origin, so we have to add a constant onto our re to the I theta type term to offset the center of the circle. So on C4, z is a plus small r e to the I theta, because a is just the center of the small circle right there. And we are going to be, remember, taking the limit as small r goes to 0, shrinking those small circles down to 0 size. Again, we want to consider the modulus of z f of z, because if we can show that this goes to 0, then we've shown that the line integral over C4 goes to 0. So let's see what happens. The modulus of z as r goes to 0 is just going to be a, because the r e to the I theta term goes to 0. So we start with a times something. Now I'm going to look at this factorized version of f of z for evaluating f of z on C4. The first term on the numerator is a plus z. That's the same as 2a plus r e to the I theta. And again, that's going to go to just 2a, because the r e to the I theta term goes to 0. So that's 2a to the power of a half, first of all. What about the a minus z bit? Well, that's going to be a minus r e to the I theta. The a's cancel and you're going to end up with just minus r e to the minus I theta. And again, because we're taking the modulus, that is a complex number whose modulus is just r. So we get r to the power of a half. On the denominator, we've got a plus r e to the I theta minus b. Again, the r e to the I theta term becomes negligible. And so it's roughly just a minus b cubed. I suppose that should really be the modulus of a minus b cubed, strictly speaking, because this should all be positive and b is bigger than a. But in any case, we can say that the only r dependent part of this in the limit when r goes to 0 is on the numerator, and therefore the whole thing goes to 0 as r goes to 0. And not surprisingly, much the same thing happens if you parameterize C6 in a similar way. You can say C6 on C6, z equals minus a plus r e to the I theta. Plug that in to your factorized form of f of z, and you'll be able to show that there's just an r to the half term on the numerator, and the whole thing goes to 0 as r goes to 0. So just to summarize, the key result that we've derived so far is that the contributions to our contour integral on the segments of the curve C1, C4, and C6 all go to 0 in the limit where the small circles become very small and the large circle becomes very large. I'm also going to add in the fact that the integral over C2 plus the integral over C8 is 0. In other words, the integral on this downwards vertical line cancels out the integral on the upwards vertical line, and it's quite easy to see why that is. If you imagine what value z takes on both C8 and C2 in the limit, as we shrink that gap between them down to 0, we're going to get z equals iy, where y is a real parameter. In other words, z is purely imaginary. There's no branch cut on the imaginary axis, and therefore f of z has the same value immediately to the left and immediately to the right of the imaginary axis. And so the only difference between the integrals on those two parts of the curve is that the limits on C8 are going to be from 0 to infinity, while the limits on C2 are going to be from infinity to 0, and therefore we just acquire a minus sign, and the two integrals are going to cancel each other out. So that just leaves us with C3, C5, and C7, which are not 0 and which are not going to cancel out, and that's where the interesting stuff is going to happen. The main difficulty that we're going to have is that we need to sort of face the multi-valuedness of f of z and think carefully about what sign the power of a half in f of z is going to give us, both above and below the branch cut. So what we're going to do is simply to choose the branch of f of z such that, as I've written here, a squared minus z squared to the half is the positive square root of a squared minus x squared on C7/C3, in other words, just above the branch cut. Notice in particular I've switched from z here to x here to emphasize that on C7 and C3, in other words, just above the branch cut, or indeed just below the branch cut on C5 as well, z is essentially just a real number as we shrink down those circles. In other words, the imaginary part of z is going to become negligibly small, and we can say z equals x, where x is a real number. Now, it's totally fine to just choose f of z this way and just say we are going to force it to be positive in this particular region of the complex plane, as long as we're consistent about the sign that f of z has in the various other regions of the complex plane, in particular along the line C5 and at the pole which is x equals b, or z equals b on the real axis. The conclusion of that is that the integral of f of z over c7 plus the integral of f of z over c3 just becomes I, in other words, the original integral, real integral that we are trying to evaluate, in the limit when small r goes to 0, those circles shrink down, because then the limits of integration, if you go from the beginning of c7 to the end of c3, the limits are just going to become minus a to a, because we've defined f of z such that the numerator of f of z is just the square root of a squared minus x squared, if you're immediately above the branch cut, and that matches up perfectly with what we have in our original integrand. We're also sort of implicitly taking the limit in which c2 and c8 are getting squeezed in closer and closer to each other, and saying that the integral over c7 plus the integral over c3 is just the same as integrating along one big straight line immediately above the branch cut. If you wanted to show that a little bit more formally, you could say that the limits of integration on curve c2 are from minus a plus lowercase r up to minus epsilon, where epsilon is a small quantity and defines where this point here is on the real axis, and then the limits of integration along c3 would be positive epsilon, in other words here, up to a minus r, in other words here, and then you take the limit as r goes to 0 and epsilon goes to 0, and you show that it's equivalent to just integrating along one big line. But you can kind of see that we're not going to have any issues in doing that, because there are no branch cuts on the imaginary axis and there are no poles on the imaginary axis, and so we can just straightforwardly take the limit and join those curves together. So if we go back to this big equation, which said that all of the various integrals added together is 2 pi I times the sum, or well, 2 pi I times just the residue at b. Most of the integrals are 0, some of them cancel out. We've shown that the contribution from c7 and c3 combined is just I, under this convention that we've chosen for the branch of f of z, and so the whole thing reduces quite nicely to just I plus whatever the integral over c5 is equal to 2 pi I times the residue at b. So c5 is the only part that we haven't really looked at in detail, and so that's going to be our next step. So how are we going to work out the integral over c5 in terms of I? Well, the key observation is going to be that as you traverse the curve c4, right, in other words, you go from this point here, the start of c4, all the way around to the end of c4, you're circling around the point z equals a, and therefore the complex number z minus a changes in phase by 2 pi, because you're going a full circle clockwise around point A. If z minus a gains a phase of minus 2 pi, then a minus z also gains a phase of minus 2 pi, because a minus z is just the same thing but with a minus sign in front of it. So this part of f of z changes in phase by minus 2 pi, so it's going to pick up an extra factor of e to the minus 2 pi I. Well, the first factor on the numerator, a plus z to the half, is not going to change at all, because when you move around c4, you don't circle around the point minus a, hence z plus a or a plus z does not change in phase. How can we write that out a little bit more quantitatively? Well, if we say that on c7 and c3 f of z is as defined here, then we can say that on c5, having traversed all the way around c4, f of z is almost the same thing but with an additional phase factor, which is going to be e to the minus 2 pi I to the power of a half, because this term here, the a minus z, is gaining a phase factor of e to the minus 2 pi I, and that whole thing is being raised to the power of a half. And e to the minus 2 pi I to the half is, of course, e to the minus pi I, which is just minus 1. And therefore, we conclude that the sign of f of z is opposite just above and just below the branch cut. If you'd like to see that demonstrated a little bit more rigorously, then take a look at my previous video. Now remember that earlier on we defined f of z, we chose the branch of f of z in such a way that the power of a half is the positive square root on c7 and c3, and therefore, because we've just argued that on c5 f of z differs by a factor of minus 1, all you need to do to find out f of z on c5 is stick a minus sign in front of the square root. That has a very important consequence relating the integral over c5 to the original integral I. Notice that the integral over c5 has the opposite sign for the integrand, but you're also traversing the path in the opposite sense, right? The limits would be from a to minus a instead of from minus a to a along C5. And so because you've reversed both the limits of integration and the sign of the integrand on C5 compared with C7 and C3, you've got two sign changes that cancel each other out, and therefore the integral over C5 is in fact just I as well. So it turns out to be a very simple result actually, but it requires some quite careful justification to show why it's equal to I. Then we go back to this result here and notice that the left-hand side simply becomes 2I. So here's where we've got to. We can, of course, just cancel a 2 from both sides, and therefore our only remaining task is to calculate the residue of f of z at the pole at z equals b. To calculate that residue, we are going to use the standard derivative formula for an nth order pole, which I have quoted here for a generic pole at z equals z0. I'm not going to prove that here, but it's a sufficiently standard result that you can go and look up a proof of it if you are interested. So what we want to do is just apply that general formula to our pole at z equals b. So the residue at b is going to be equal to the limit as z goes to b, right? Z0 is just the location of the generic pole. N in this formula is the order of the pole. We've already said earlier that it's a third order pole because z minus b is cubed there on the denominator. So it's 1 over 2 factorial. 2 factorial is just 2. So we get a half there. It's going to be a second order derivative because it's a third order pole. Then we've got z minus b to the 3, z minus b cubed multiplied by f of z, which just makes the denominator disappear and just gives you a squared minus z squared to the half. So let's do the derivatives one at a time. We have got our prefactor of a half, which is just going to stay there. I'll keep one factor of d by dz there, and we'll differentiate a squared minus z squared to the half once. That is going to pull down a factor of a half, so you get half a squared minus z squared to the minus a half. Then you use the chain rule to get an additional factor of minus 2z. I'm just going to put a little b there to remind us that we're going to take the limit as z goes to b later on. So then we can just cancel this half with this 2 and put the minus sign at the front to make it look a little bit nicer. And so this is going to be minus a half d by dz of z a squared minus z squared to the minus a half, evaluated as z goes to b. So to do the next derivative, we of course have to use the product rule because you've got z multiplied by all of that stuff there. So we're going to have minus a half. First of all, let's differentiate the z and keep the more complicated function. So we've got a squared minus z squared to the minus a half. Then we're going to keep the z and differentiate the more complicated function. That's going to bring down a minus a half. You've still got that z sitting there. You've got a squared minus z squared now to the power of minus 3 halves because you've differentiated, and you've got yet another minus 2z from the chain rule, and all of that evaluated as z goes to b. Now it becomes a bit easier to see what to do next. If we write our negative indices as fractions instead, then you can see that the denominators of those two fractions, this and this, are quite similar, but they differ by a power of 1, basically, which means if we want to make the denominators the same so that we can add them, we need to multiply the first fraction by an additional a squared minus z squared to the power of 1. So this one is going to turn into just a squared minus z squared, and then we can turn that power into 3 over 2, so the denominators are the same. And then this is great because when you add them, this z squared will cancel with this z squared, and you are left with minus a half a squared over a squared minus z squared to the 3 halves. Remember, this is all in the limit as z goes to b. So we know that I is pi I multiplied by all of this stuff, but there's one more potentially unexpected complication that we have to think about, which is what is the sign of a squared minus z squared to the 3 over 2 in the region of the complex plane where z equals b. Again, because it's a fractional power, we have issues with multi-valuedness, and we have to choose the branch in a way that's consistent with the sign choices that we made earlier. We can already see that because b is bigger than a, if we do a squared minus b squared and then do the whole thing to the power of 3 halves, you're going to get an imaginary quantity, but the question is it positive imaginary or negative imaginary? Now, to figure it out, we are going to split up the denominator into two factors. We're going to write it as minus a half a squared over a squared minus b squared. At this point, I'm substituting b in place of z, so a squared minus b squared, and then a squared minus b squared. Again, this time to the power of a half, so you've got 3/2 power in total. Now, to figure out the sign of that 1/2 power, we are going to use some similar phase-related arguments relating to z minus a to what we did earlier in the video. So remember that we have chosen the branch of f of z in such a way that on C7 and C3, just above the branch cut, a squared minus z squared to the half is the positive square root of a squared minus x squared, and I've switched from z to x to emphasize that z is essentially real there. So how does that relate to a squared minus z squared to the half in the part of the complex plane where z equals b? So let's just write out here a squared minus z squared to the half. Well, first of all, its magnitude is clearly going to be the square root of x squared minus a squared, or b squared minus a squared specifically, but more generally, if you're on the right hand side of the real axis, it's going to be magnitude of x squared minus a squared. It's going to be e to the I times something. What is that phase? Well, as you traverse from here to here, you're sort of moving in a semicircle like that and acquiring a phase of minus pi. You're going half a circle in the clockwise direction, which is the negative direction in terms of phase, which means z minus a is going to pick up a phase factor of e to the minus I pi. Z plus a is not going to pick up any additional phase factor because you're not circling around z equals minus a, and so we get an extra phase factor of e to the minus I pi, but then that whole thing is square rooted, and e to the minus I pi over 2 is minus I, so that is minus I times the square root of x squared minus a squared. The conclusion is that to be consistent with the signs that we chose earlier in the video, we need to make this quantity here negative and imaginary. Again, if you're not fully convinced by my argument of moving around in the complex plane in certain terms acquiring extra phase factors, do have a look at my previous video to see that proved in a little bit more detail. So finally, we can put all of this stuff together and come up with the value for our integral. So we've got minus a half at the beginning. We've got a squared there. I am going to write a squared minus b squared as minus b squared minus a squared, because we know b is bigger than a, and that is then a positive quantity. Then we have minus I times the square root of b squared minus a squared. Remember, that's what we were discussing up here, right? So I'm going to stick the minus I there, and I'm going to put the square root of b squared minus a squared there. Then some minus signs are going to cancel. This and this are going to cancel. Then you've got minus I on the denominator. 1 over minus I is just I. And so this just simplifies to I over 2 times a squared over b squared minus a squared times the root of b squared minus a squared. And then don't forget, we have to times that whole thing by pi I. Multiplying by I will just make this I turn into a minus 1, and then we get an extra pi on the numerator. So our conclusion is our integral I is equal to minus pi a squared over b squared minus a squared times root of b squared minus a squared. As we said earlier, this is a positive quantity. The square root by definition is a positive quantity, and so we can clearly see that I is negative. That makes a lot of sense when you think about the sign of the integrand up here in the region that we are integrating over. So x is always between minus a and a, but b is bigger than a, and therefore x minus b is negative. X minus b cubed is always negative in the region that we're integrating over. Therefore, I should indeed be negative. So that's all. If you have been watching my channel for a while, you might be a little bit surprised to learn that this integral, as far as I know, doesn't have any particular application in physics. It's just a cool integral that I came across, but I thought I just enjoyed the process of solving this too much not to make a video on it. So if you've made it this far, I hope you have found this interesting as well, and I will see you again soon.